In this video, we are going to look at geometric sequences and the explicit and recursive formulas for geometric sequences. So the first question is, what is a geometric sequence? Well, we've been studying arithmetic sequences where each term after the first is found by adding a constant to the previous term. And that constant that we're adding, we'd call that the constant difference, because if I take any term and subtract the previous term, I would get that value. In a geometric sequence, each term after the first is found by multiplying the previous term by some constant. So if I actually look up here, the first row has one person, the second row is 2, the third row has 4 people, the fourth row has 8 people. This sequence would actually be a geometric sequence, because to get from the previous row to the next row, I'm multiplying each time by 2. This is what's called a constant ratio, because if I take any term and divide it by the previous term, or if I find that ratio, which means divide, that's how I get that multiplier of 2. So arithmetic sequences, there's a constant difference found by subtracting consecutive terms. Geometric sequence, there's a constant ratio, which you get by dividing consecutive terms. So now let's take a look at 4 different sequences. I'm wondering which of these sequences are geometric, and for any that are geometric, can we find the constant ratio? Let's look at the first one together. What do you think? Is this geometric? It actually is. If you take any term and divide it by the previous, so the fourth term divided by the third, or the third divided by the second, or the second divided by the first, I should get out the same value every time, which is 3. That's your constant ratio. Meaning if I start at 12 and I multiply by 3 repeatedly, that's how I would generate the next term in the sequence. Pause the video and see if you can determine which, if any, of the next sequences are geometric. The last sequence was actually the only other one that was geometric. If you take any term divided by the previous, you should get that constant ratio of -11. So if I start at -1/2 and I multiply by -11 repeatedly, that's how I would generate the next terms in the sequence. So the first sequence and the last sequence are geometric. Now perhaps you recognize the second sequence as arithmetic, and you should be able to find the constant difference. So if I take any term and subtract, which is what that difference means, and subtract the previous term, I should get a constant difference of 26. Meaning if I start at the first term and I add 26 on repeatedly, I'd get the next term. So since there's that constant difference, I'm adding the same amount every time. The second sequence is arithmetic. Now, the third sequence, this actually isn't geometric, and it's not arithmetic either. I know it's not geometric because if I take any term divided by the previous, so the third divided by the second, or the second divided by the first, I'm not getting out the same number. So since these aren't the same, this can't be geometric. If I take any term and subtract the previous term, so the second minus the first, or the third minus the second, if I take any term and subtract the previous term, I'm not getting the same amount either, so it's not arithmetic. Is this a sequence? Sure. I mean, I'm adding on 3, then 5, then 7, then 9. There's a definite pattern here. I'm adding the next odd number, or actually this is 1 squared plus 1, 2 squared plus 1, 3 squared plus 1, and so on. So this is a sequence, but it's not geometric because I don't have that constant ratio. It's not arithmetic because I don't have the constant difference. Now this is an example. I give you the first term in the sequence and the fifth, and I want you to fill in these middle 3 terms to make this sequence arithmetic. and then fill it in with 3 different terms to make the sequence geometric. Pause the video and give this a try. Now, this may have been my train of thought. If I want to make this sequence arithmetic, I'm starting at 16, and to get to the 5th term, I would have to add on that constant difference 5 minus 1, or 4 more times. And adding on that constant difference 4 times is what should get me to the 5th term. So if you solve this, subtract 16, divide by 4, let's see, you get 152 and a quarter. So if I add 152 and a quarter onto 16, I'd get the next term. Add on 152 and a quarter again. Add 152 and a quarter. Add 152 and a quarter, and I should be to the 4th term. Or 5th term, excuse me. Now, maybe you approach this a different way. Another way to find that constant difference is what we talked about with slope in a previous video. The first term, 16, the 5th term is 625. So if you plug these into the slope equation, y minus y over x minus x, that would also generate the constant difference. So if I know this is an arithmetic sequence, I'm adding the same amount every time. I have that same rate of change, constant rate of change. That means the slope should be the same between any 2 points. If I want to make this a geometric sequence, I might follow, kind of a similar train of thought, but I want to multiply by some value repeatedly. So now my equation would look like, well, I'm starting at 16, and I'm multiplying by some constant ratio 4 times, and that should give me out 625. So r to the 4th should equal 625 divided by 16. How do I get rid of the 4th power? Well, I would raise this to the 1/4 power, or take the 4th root. So if I take the 4th root, or raise 625 over 16 to the 1/4 power, I should get out 2.5. Now, did anyone catch this? If I have r to an even power and I take the 4th root, or the 1/4 power, I should actually put out front that plus or minus sign. So r here could be 2.5 or negative 2.5. So if I multiply by 2.5 repeatedly, so I'm starting at 16, multiplying by 2.5 over and over and over again, those would be my 2nd, 3rd, and 4th terms of the sequence. Now, if I started at 16 and multiplied by negative 2.5, I'd get negative 40, times negative 2.5 would give me positive 100, times negative 2.5 would give me negative 250, times negative 2.5 would give me positive 625. So actually, these middle terms could be the positive or negative for the 2nd and 4th terms. Now, hey, just another interesting side tidbit here. There's something that's called an arithmetic mean and the geometric mean. So the arithmetic mean, if I want to find 2 numbers, or the number right in between 2 numbers in an arithmetic sequence, that's what you know as finding the average. So I'd add 2 numbers, divide by 2. That mean that we've been talking about, that is the arithmetic mean if I add and divide by 2. There's also something called the geometric mean. So if I have a geometric sequence and I want to find the number right in between 2 numbers in a geometric sequence, the geometric mean you would actually find by multiplying the numbers and taking the square root. And that's another way to get that term that's right in the middle of 16 and 625 in a geometric sequence. Okay, so then this leads us to the recursive and explicit formula for a geometric sequence. So the recursive formula for a geometric sequence, I still need to know where to start, so I'd list whatever the first term is. And then to find the nth term, well, recursive I'm relying on the previous term, and I'm going to take the previous term times some constant ratio, which I'm going to call 1. And this is how I would calculate any term beyond the first term. The explicit formula, if I want to calculate the nth term directly, so if I want to calculate the 100th term without relying on the 99th term, I could take the first term and I'd multiply by that constant ratio n minus 1 times. Or again, if I want to find the 100th term, I'd take the starting term and I'd multiply by the ratio 100 minus 1, or 99 times, because the 100th term is 99 terms after the first term. So this is your recursive and explicit formulas for a geometric sequence. Very important, make sure you have these recorded somewhere. So now let's see how you can do. Here is a geometric sequence. Write an explicit formula and a recursive formula for this sequence. Just a hint, you're going to want to find the constant ratio, and then you're going to need to know the first term, which is actually given for you. Pause the video, give this a try. So to find that constant ratio, if you took any term divided by the previous term, so the fourth divided by the third, or the third divided by the second, or the second term divided by the first, you should get out the same number for all of these ratios, which is negative 0.2, or negative 1/5. So that's your constant ratio. If I want to write the explicit formula, well, I know where I'm starting. The first term is 6, so a sub 1 is 6. And then to get to the nth term, I'm going to take the previous term and multiply by that constant ratio, which is negative 1/5. And that'd be to calculate any term beyond the first term. If I want the, oh, that was the recursive, I guess. So I just did part B. If I want the explicit formula, to get the nth term, I'm starting at 6. And I'd be multiplying by 1/5. Careful, did you get this? N minus 1 times. If I want the 100th term, I'd only be multiplying by that negative 1/5 99 times, because the 100th term is 99 terms after the first term. Last example, I've given you a recursive formula for a sequence. Find the first 5 terms of the sequence, write them down, and then write the explicit formula for the sequence. Pause the video, and then we'll check to see how you're doing. So to find the first 5 terms, here's the first term, and then the second line of the recursive formula is telling me I need to take the previous term and multiply by 3/4. So if I multiply by 3/4 over and over and over again, feel free to use your calculator. That should give you the first 5 terms of the sequence. Explicit formula to calculate the nth term. I'm starting at 80, and I would be multiplying by 3/4 n minus 1 times. So, I mean, take a look here. To get the 5th term, I multiplied by that constant ratio, not 5 times, but 4 times, because the 5th term was 4 terms after the first term. So that's your explicit formula. Now, let's say I asked you to find the 25th term of the sequence. Would you use the recursive or the explicit formula? Well, I definitely use the explicit formula. I don't have to rely on the 24th term to find the 25th term. So to find the value of the 25th term, I'd start at 80, and then I'm multiplying by that 3/4, 25 minus 1, or 24 times, because the 25th term is 24 terms after the first term. Now this would give you out about 8/100ths. So as I progress in the sequence, the values are getting smaller and smaller and smaller. If you kind of graph these points, so the first term's 80, the second term is 60, the third term is 45, and each term is 3/4 the previous term, if you graph these, where n is on the x-axis, that's the term number, the value of the term is the y-axis, you should see some exponential decay. So if I connected this graph, it should look like those functions that we studied previously in the year, y equals a times b to the x power. So arithmetic sequences have that linear relationship. If you plot the points, connect it, you get a line. Geometric series, you should see that exponential relationship. If you plot it, you get an exponential function.